Hello, everyone. Welcome to Physics 205. So the next couple of lectures are going to deal with objects that are in equilibrium. This first lecture is going to talk about objects that are in what's called translational equilibrium. So basically, objects that are either at rest or moving with a constant velocity are said to be in translational equilibrium. Okay, and actually most of the cases that we deal with will be objects at rest, but also if the object is moving at a constant velocity, that's also considered to be translational equilibrium. Now remember, if an object is at rest or moving at a constant velocity, then that means its acceleration, right, which is a change of velocity over change in time. Well, if the velocity is constant or zero, that acceleration must be zero. Okay, so the key thing here is objects that are in translational equilibrium have an acceleration of 0 meters per second squared. So then if you apply Newton's second law, remember Newton's second law says that the sum of the forces is equal to ma, mass times acceleration, but the acceleration is zero, that means that the sum of the forces must equal zero. So anytime that an object is in translational equilibrium, the sum of the forces is equal to zero. Now, if we have a coordinate system and we write this in terms of the components, then we can write this vector equation, right? The sum of the forces, these are all vectors, the forces here is equal to zero. If we find all the components of all the forces acting, then we can split this up into two scalar equations. One that is simply the sum of the forces in the x direction has to add to zero, and the sum of the forces in the y direction has to add to zero. And this set of equations right here is called the first condition for equilibrium. Okay, so if an object is in translational equilibrium, then this is true. The sum of the forces in each direction must equal zero. So this is how we're actually going to solve the problem, by setting the forces in the x direction equal to zero and setting the forces in the y direction equal to zero. Okay, so let me do a couple of examples with this. Okay, so in this example, you're told that 150 Newton bird feeder, so they're giving you the weight of the bird feeder, it's 150 Newtons, is supported by 3 cables, as shown in this picture, and we want to find the tension in each cable. So basically, we want to find the tension in this cable, I'll call it like T1, the tension in this cable, T2, right? So these are the forces, and then the tension in this cable, call it T3. So we want to find those values of T1, T2, and T3. Now notice that this knot here, where those cables all meet, this knot is in equilibrium, right? So this knot right here is in equilibrium. It's not moving. It's not moving in the y direction, not moving in the x direction. It's just stationary, right? So therefore, that knot must be in translational equilibrium. And we can apply the fact that the sum of the forces should equal zero to solve this problem for those 3 tensions. Okay, so we need a coordinate system. Probably the easiest coordinate system to give in this case would be the standard coordinate system, where x is to the right and y is vertical. So that means if I let me draw a coordinate system like right through the knot here. So this would be like the x-axis, and then this would be the y-axis. Okay, so here I'm going to draw this picture again because now we need to find the components, right, of each of those forces. So I first have T1. I don't know what the magnitude is of T1. That's what I'm trying to find. But I do know that this angle right here is 30 degrees. How do I know that? If you go back to this picture, right, this regular picture, these two lines are parallel. And you can think of this cable as like what's called a transversal that passes through. And it turns out that this angle and this angle have to be equal, right? Those are called alternate interior angles. So if this is 30 degrees, this also has to be 30 degrees. Okay, T2 is going to look something like this. Where in this case, let me go back to this picture here. Again, if this is parallel to this, this is like your transversal, then that means this angle is equal to this angle, right? These are alternate interior angles. So this angle must be 60 degrees, which is really like the reference angle. So over here, I'll draw that as 60 degrees. And in T3 is it's acting straight down, right? In a negative y direction. This would be like T3. Okay, so what I want to do is I want to find the components, right? I want to find T1x. So if I project T1 onto the x-axis, this is going to be T1x. Project T1 onto the y-axis. This will be T1y. T1y. Project T2 onto the x-axis. This is like T2x, which is going to be negative in this case. And then project T2 onto the y-axis. And this right here will be T2y. And same thing with T3, but T3 is really only going to have a y component in this case. Okay, actually, let me start with T3 because T3 is going to be the easiest one to solve for. If you look at the picture here, let's focus now on that feeder, right? So the feeder, I'll draw it right here. Let me draw a free body diagram. Well, what are the forces acting on that feeder? We have the weight of the feeder acting down. Let's call it W, weight of the feeder. And then that tension at T3 is acting up on the feeder. Okay, so if I choose a coordinate system, which I'm just going to use my standard XY coordinate system here. So there's no forces even acting in the X direction. I'm not going to worry about the X direction, but let me apply Newton's second law to the Y direction. So I have sum of the forces in the Y direction is equal to 0. Remember, it's in translational equilibrium, so the sum of the forces are always going to equal 0. So in this case, I want the Y component of T3. I want the Y component of the weight, and that's got to equal 0. Well, the Y component of T3, since the entire T3 is acting in the positive Y direction, then this is going to be plus T3, right? It's all of tension 3. It's acting in the Y direction. And then the weight is all acting in the negative Y direction. So the Y component of the weight is minus the entire weight, so minus W, which normally we write as mg, but in this case, they're giving us, right? They gave us that weight value as 150 newtons. So I'll just leave it as W, and that's got to equal 0. Now, if I add W to both sides, then I find here that T3 is equal to the weight, but we already know that value. It's 150 newtons. Okay, so one of the tensions is done. T3 is simply equal to the weight of that feeder, which kind of makes sense, right? So T3 is going to be 150 newtons. All right, now let's see if we can find T1 and T2. So let me go back to this picture over here. And let me apply Newton's second law. I'll start with the X direction. So sum of the forces in the X has to equal 0, right? Because that knot is in translational equilibrium. Okay, so I want the X component of T1. I want the X component of T2. And then the X component of T3. And that's got to all sum to 0. Well, what is the X component of T1? Well, if you look at that picture, right, if this is, let me draw the triangle here. So this is T1, right, the hypotenuse. We know this is 30 degrees. This is T1x. This is T1y. So because T1x is adjacent to 30 degrees, it's going to involve cosine, right? Or here, I'll do it out carefully the first time. So I know that cosine of 30 must equal the adjacent side, T1x, divided by T1, right? Divided by hypotenuse, right? Cos, SOHCAHTOA. So if I solve for T1x, I want to find that T1x is equal to T1 times cosine of 30 degrees. So T1x, and it's positive, right? Because it's pointing towards the right here. So T1x is going to be T1 times cosine of 30 degrees. Okay, what about T2x? Well, T2x, I'm going to use this triangle where that's my right triangle, right? This is T2, the hypotenuse. This is 60 degrees. This is T2x, which happens to be negative. We're going to make sure we take that into account later. And this is T2y. And again, because the T2x is adjacent, right next to the 60 degrees, it's going to involve the cosine. So the x component of T2 is going to be minus T2 times cosine of 60 degrees. And then what is the x component of T3? Well, T3 is all in the negative y direction, right? There's no x component of T3. So that's just going to be 0 is equal to 0. Okay, so this equation just says that T1 times cosine of 30 minus T2 times cosine of 60 is equal to 0. Let me like box that. So we keep that in mind here. So that's our first equation. Okay, I'm going to do the same thing now, but for the y direction. So now I want to sum the forces in the y direction and set them equal to 0. So I have sum of the forces in the y direction is equal to 0. So now I want the y component of T1 plus the y component of T2 plus the y component of T3. And that's got to equal 0. Well, what's the y component of T1? Again, if you look back over here at this picture, this is opposite 30 degrees, right? So sine of 30 is going to be opposite over hypotenuse. So if we rearrange that, if we solve for T1y, it's going to be T1 times sine of 30. And same thing over here. If I look at T2, right, since this is opposite the 60 degrees, then T2y is going to be T2 times sine of 60. And in both cases, since those components are pointing upward, they're both positive. Okay, so T1y is going to be T1 times sine of 30, and that's positive. T2y is going to be T2 times sine of 60, and that's positive. And then T3y, well, how much of T3 is in the y direction? All of it, and it's negative. So this is simply going to be minus T3 is equal to 0. So that's really like our second equation. And we know something about T3. We already found T3 over here, right? Remember, T3 is 150 newtons. So I could plug that in. Actually, let's do that right now. So I have T1 sine of 30 plus T2 sine of 60 minus 150. T3 is 150. That's got to equal 0. Okay, now notice here that we basically have two equations. So one linear equation, another linear equation, and two unknowns. We don't know T1 and T2, right? Remember, T3 is already known, it's 150. Really, let me box this one. And this is the one we want to use right here. So this one and this one, right? Those are two equations by two unknowns. And we know cosine 30 and cosine 60 and sine of 30 and sine of 60, we can just plug that into our calculator, right? Those are just decimal values. So those are known. The only two things we don't know are the tensions, T1 and T2, those two magnitudes. So I'm going to write this one more time, but I'm going to plug in the values for sine of 30 and cosine of 30, and then sine of 60 and cosine of 60. So this first equation here, I'll write as T1. Now, cosine of 30 degrees is the same as 0.866. So this is 0.866. Then I have minus T2 times cosine of 60, which happens to be a half, so 0.5. That's got to equal 0. And then if I do the second equation, I have T1 times sine of 30, which is a half, plus T2 times sine of 60, which is 0.866, and then minus 150 is equal to 0. Okay, so those are our two equations by two unknowns. Now, how do we solve them? Well, usually what we do is we line these things up, right? We keep the first variable t1 lined up on the left-hand side, t2 lined up, and then we put all the constants on the right-hand side. So here, I'm going to do that on the next page. So I'm going to line everything up. Actually, what I'll do too is I'll usually write the coefficient, the number in front of the variable. So same thing, I'm just going to write it slightly differently so we can solve it more easily. I'm going to write it like this. So I have 0.866 t1 minus 0.5 t2 is equal to 0. And for the second equation, it'll be 0.5 t1 plus 0.866 t2 is equal to, and I need to add the 150 to both sides, so I'm going to have positive 150 on the right-hand side. Okay, so the question is, how do we solve these? Well, remember, there's multiple ways you can do this. You probably learned this in college algebra or in high school algebra. You could use elimination. You could try to eliminate one of the variables. You could use substitution. If you know some linear algebra, there's different matrix methods you could use. You could use determinants. You could use Gauss-Jordan eliminate. Like there's many different ways. Probably the ones that you're most familiar with are elimination and substitution. Let's do elimination. Well, to eliminate one of these variables, right? And let's say I want to eliminate t2 here. Right now I have a negative 0.5, right, as my coefficient of t2 in the first equation, and I have positive 0.866 as my coefficient of t2 in the second equation. I want to make these coefficients equal but opposite, right? One positive, one negative, but equal so that when I add the equations, the t2 disappears. Well, to do that, I could multiply this first equation by 0.866, and I could multiply the second equation by 0.5, right? And then that'll make those two equal but opposite. But you can't just multiply part of the equation by 0.866. I have to multiply the entire first equation by 0.866. So let's do that right here. So I'm going to multiply 0.866 by this entire equation. And remember, you have to multiply both sides by 0.866. So don't forget to multiply the right-hand side. And for the second equation, I need to multiply that equation by 0.5. And again, don't forget to multiply both sides. Right, so I also have to multiply that by that 150 by 0.5 as well. Okay, so if you do this, right, so I'm going to distribute these values in now. You're going to get, so 0.866 times 0.866 is 0.75 T1 minus, and if I do 0.866 times negative 0.5, I'm going to get negative 0.433 T2. That's equal to 0 times 0.866, which is just 0. And then in the second equation, 0.5 times 0.5 is 0.25 T1. And then 0.5 times 0.866 is positive 0.433 T2. And that's equal to 0.5 times 150, which is half, right? 75. Now remember, the reason why I did this is so that these two would match but be opposite, right? So by multiplying that first equation by 0.866 and the second equation by 0.5, I was able to get these to be equal but opposite. Now I can add these two equations together, right? The T2s are going to disappear. 0.75 T1 plus 0.25 T1 is just 1.00 T1. And that's equal to 75. This case, there's no other work, right? Normally you have to divide by the coefficient, but it's already 1 times T1, which is T1. So this is telling us that T1 is 75 newtons. Okay, so we got T1. How do I go back and find T2? Well, I plug back into one of these two equations here. I can use either one. Maybe the first one's a little bit easier. So for that first equation, I have 0.866 T1 minus 0.5 T2 is equal to 0. So let me solve that for T2. Let me first just add it to both sides to bring it over to the right-hand side. So I'm going to have 0.866 T1 is equal to 0.5 T2, and then I'll divide by 0.5. Right, so this cancels, and I get T2, I want to write it on the left-hand side now, is equal to 0.866 over 0.5 times T1. But I know what T1 is. T1 we just found was 75 newtons. And if you work that out, you're going to find this is 129.9 newtons. So T2 is equal to 129.9 newtons. And then we're done, right? We have all three tensions now. We know T1 is 75 newtons, we found here. T2 is 129.9. If we go back, remember we found T3 right at the beginning is 150. So we know all these tensions. So those are the correct tensions so that that feeder just stays static right there. That knot is not going to move. It's in translational equilibrium. Okay, now were there other ways of doing this instead of using elimination here? Yeah, you could use substitution, right? You could have solved for one of the variables in terms of the other and then substituted it in. That will also eliminate it. So it's up to you. I just did the example in terms of using elimination, but if you want to use substitution, that will work as well. Okay, actually here, let me do substitution really quick just to show you how it works. I'll have to go on another page here. So, all right, could have also used substitution. Right, to solve those two equations by two unknowns. So remember the equations were this, it was 0.866 T1 minus 0.5 T2 is equal to 0, and then 0.5 T1 plus 0.866 T2 is equal to 150. So we could have chosen one of the variables to solve for in one of the equations. So in that first equation, let's solve that for T1. So if I take this first equation, and I solve for T1. So I'm going to add 0.5 T2 to both sides. So I'm going to get 0.866 T1 is equal to 0.5 T2. I'll divide by 0.866. Whatever I do to one side, I have to do the other side. So you're going to find that T1 is equal to, if you do that division there, it's going to be 0.577 T2. Okay, so now what you do is you take that expression that you just found for T1 and you substitute it into the other equation. So where I have a T1 in the other equation, the second equation now, I'm going to plug in 0.577 times T2. So then that second equation now becomes 0.5 times, and I'm plugging in 0.577 T2 plus 0.866 T2 is equal to 150. And now notice that equation is entirely in terms of T2, so I can solve it for T2. if I multiply, right, we're going to distribute that 0.5 in, I'm going to get 0.2885 T2 plus 0.866 T2 is equal to 150. Those are like terms, right? I can add these two terms, I can add together. They're like terms. So if I do that, I'm going to get 1.1545 T2 is equal to 150. And then finally, I can divide to get T2, since it's being multiplied by 1.1545, I need to divide by 1.1545, right, to get a 1 here. But whatever I do to one side, I better do the other side. And you're going to find that T2 is equal to, it better be, right, 129.9. And then if I go back, I can plug back in, and probably the easiest one to plug back into is the one that I already manipulated here. Remember, I solved for T1 in terms of T2 right there. So if I plug T2 back into that equation, so I'm going to plug back into here, then I can find T1. So in this case, T1 is equal to 0.577 times 129.9. And if you work that out, of course, you're going to get 75 newtons. So there's multiple ways that you can solve these systems of equations if you end up with a system of linear equations. But the two most common ones are the two that we just showed you, elimination and substitution. Okay, let's do one more example with translational equilibrium. And then eventually we'll move into something called rotational equilibrium. That'll be the next lecture. But let me do one more example here. Go back to this page. Okay, so in this example, it says two blocks are connected by a string as shown below. Find the mass of the hanging block. So we want to find this mass, what this has to be in kilograms, such that the system is in equilibrium. And we're assuming that the surface here that the block is riding on is frictionless, right? So we don't have to add any frictional forces here. Okay, so we're assuming this is not moving, right? It's in equilibrium, and we want to find the mass of that block such that the whole thing remains in equilibrium. Okay, so a couple of things. We're given the mass M1, right? It's 6.7 kilograms. So we could find its weight. Let's just do that right now. So we know that the weight one will be M1 times G. So this is going to be 6.7 times 9.8. So that turns out to be 65.7 newtons. Okay, I'll start with that. And then I want to draw all the forces acting on each object. So let me start with the block that's on the ramp there. Well, there's several forces acting, right? We have the weight that we just calculated acting down towards the center of the earth. So that's like weight one. We have the tension in the string here acting along the string, right? So along that ramp. And then we have a normal force that the ramp exerts on the block perpendicular to the ramp. So normal force like this. So that's our normal force. Okay. For the other object, this hanging mass here, we have two forces acting, right? We have the weight of the object acting down. So that's going to be mg. And then we have the tension acting up. It turns out that as long as you assume that this is a lightweight string and a lightweight pulley, that the tension you can consider to be the same throughout the string. So if we find this tension, it's the same as that tension, right? Those two tensions are equal. All right, now I need to apply Newton's second law, right, to both of these objects. But at first, I need to have some type of coordinate system. Probably in this block that's on the ramp here, I probably want my coordinate system to be oriented so that x is going up the ramp and then y is perpendicular to the ramp. So it'll be something like this. If I draw it out here, this is my x-axis, and then the y would be like this. So that would be the y-axis. So then at least the tension is right along the x-axis. So you can see the tension right along the x. The normal is right along the positive y. But the weight here is going to have components. It's going to have an x component. It's going to have a y component. Right. So the weight here, if I project this onto the x-axis, this is like W1x. And if I project it onto the y-axis, this is W1y. So the weight has components here. It turns out that if this angle is 42 degrees right here, then that's the same as this angle right here. So this angle would be 42 degrees. All right, let me redraw this. Just erase too much. So this is 42 degrees, that angle. These angles are the same. Okay, so let me start by applying Newton's second law. And remember, we're in translational equilibrium, so the sum of the forces are going to equal 0. And I'll start by looking at that first object, the M1 object. So I'm gonna reorient my coordinate system so you can see this better. So we know that the normal force, right, was pointing in the positive y direction. So this is like x and y here. The tension was pointing in the positive x direction, this. And then the weight, if you look at that drawing carefully, the weight is going to go something like that, where this angle right here is the 42 degrees. Okay, and then we want to find, that's weight 1. We want to find the x component, which is this one, W1x, and then the y component, which is this one. Okay, now you may want to, remember I said earlier, maybe a few videos ago, that you can, if you want, you can use this angle, but this is not the reference angle. The reference angle is the one that the vector makes with respect to the x-axis. And the only reason why it's sometimes nicer to use a reference angle is because then if you want to find the x component of that vector, in this case W1x, it always is going to involve the cosine. If you want to find a y component, it's always going to involve the sine. If you use this angle, then they're going to reverse. The x component, which is this, is now opposite. So that's a sine, involves sine, and the y component involves cosine. So I think it's easier just to stay consistent. So we can find this angle pretty easily, right? Because this total angle here is 90 degrees. I know this is 42. So if I do 90 minus 42, I'm going to get, what's that? 48, I guess, degrees. So this angle is 48 degrees, right? 90 minus 42 is 48 degrees. So now I can say that W1x is going to be W1 times cosine of 48 degrees. But it's negative, right? It's going to be negative because it's pointing to the left. Or you could say negative W1 times sine of 42, right? Same thing. Whatever way you feel more comfortable with is fine. So this is going to be negative. This is 65.7, right? Was the weight? Times cosine of 48 degrees, and that's going to equal 44 newtons. And then W1y, first of all, it's also negative, and it's going to be W1 times sine of that reference angle, which is 48 degrees. Or if you really want to use this other angle, then since it's adjacent, it'd be cosine of 42. Sine of 48 is the same as cosine of 42, okay? All right, so then this is going to be negative 65.7 times sine of 48 degrees, which turns out to be 48.8 newtons. Okay, let's do the sum of the forces in the x direction, sum of the forces in the y direction. So let me start with the y direction. So I have sum of the forces in the y direction, and that's got to equal 0, right? Because it's at rest. So I want the y component of the normal force plus the y component of the tension plus the y component of W1. That's got to equal 0. Well, the y component of normal force, that entire normal force is acting in the positive y direction, so that's just plus n. The y component of tension, none of that tension is in the y direction, so that's 0. And then the y component of the weight we already found was negative 48.8. Right? It's negative W1 sine of 48, which we already calculated as 48.8. So if I set that equal to 0, then I'm going to find that the normal force in this case is just equal to 48.8 newtons. Okay, it's just equal to the y component. So this force, you can kind of see it in this picture, right? This force, this normal force, is just equal in magnitude to this y component of that W1. Now let's look at the x direction. So I have sum of the forces in the x direction. Again, since it's static, it's not moving, that's got to equal 0, right? There's no acceleration, so it equals 0. So now if I do the x component of the normal force plus the x component of the tension plus the x component of the weight, that's got to equal 0. Well, how much of that normal force is in the x direction? None of it. How much of the tension? All of it, and it's positive. How much of the weight? Well, we figured it out here, right? W1x was negative 48. These should be negative, by the way. Right, that's negative, that's negative. So it's negative 44 in this case. And that's going to equal 0. Now, this is nice, right? So the only term there is the t. I can solve for the tension. So if I add 44 to both sides, I'm going to find that the tension is equal to 44 newtons. Great. Okay. So, and that's going to be helpful later. So tension is equal to 44 newtons. I don't need this today, but we also know the normal force is 48.8. Now, let me go to the other object. Remember, the other object is this hanging mass here. Let's apply Newton's second law. We only really need to do the y direction, right? There is no x direction. So I'm going to draw this out. Actually, I'll do it over here. So here's my hanging mass, and the only forces are the weight and then the tension. A really good coordinate system to use would be just x going to the right and y going vertical, right? We don't need to orient it any special way. Like the other one was easier to go along the ramp. The x was along the ramp, parallel to the ramp. In this case, the typical x is horizontal. So we'll draw it in here. X is horizontal and y is vertical. Okay, let me apply Newton's second law. Again, I don't really need to do the x direction because there's no forces acting in the x direction. So you're just going to have 0 equals 0 is going to be your equation. But let me do the y direction. So I have sum of the forces in the y direction is equal to 0, right? Because it's static, it's not moving. So now I want the y component of the tension plus the y component of the weight. That's got to equal 0. Well, the y component of the tension is the entire tension. Right? It's all t, and it's positive, right? Because it's in the positive t direction. And the y component of the weight is the entire weight, but it's negative. So negative, I'll write this as mg, because ultimately I want to find m, right? So that's equal to 0. Let me solve this for m now. So if I add mg to both sides, then I'm going to have mg, I'm going to write it on the left-hand side, is equal to the tension here. So if I divide both sides by g, then the mass here must be the tension divided by g. But we already know the tension. The tension we just calculated earlier is 44. G, of course, is 9.8. So if you work that out, you're going to find that the mass is 4.5 kilograms. And that's what we were looking for, right? We wanted to find the mass of that hanging object. So if I go back to the picture here, I wanted to find the mass of this hanging object such that this whole system was in equilibrium. Okay, and we applied Newton's second law. Well, in this case, the sum of the forces had to equal 0 because it was in equilibrium. We applied it to the block that was on the wedge here on the ramp, and we applied it to the hanging object here. And that allowed us to calculate M, the mass of that hanging object. Okay, great. So then next, what we're going to look at, we'll do a little bit more translational equilibrium, but we're going to also focus on something called rotational equilibrium, when the object is either not rotating or rotating at a constant angular velocity. In most cases, we're going to deal with situations where it's not rotating. Great, thanks.